Hello everyone, this is Nash. Today I want to show you how to calculate the total mechanical energy of an elliptical motion. You can imagine the mass, which is now written in a small letter m. It could be an Earth, which is now moving around the sun, or it can be a satellite, which is now moving around the Earth. But what is more important, it should be an elliptical motion. So our job is trying to derive the final total mechanical energy, which can be written as the minus g times mass and divided by the r1 plus r2. All right, so let's get started. First, you can start with the conservation of angular momentum. Since there's no external torque, so the conservation of the angular momentum should be conserved. And let me remind you that the angular momentum, it can be written as the r cross p, and which is r cross v and times the mass. If we take a look at the 2 points, at point A and point B, the velocity is now perpendicular to the r1 and r2 respectively. So the r cross v could be written as rv sine of theta, and the sine of theta is equal to 1. And since we're talking about the same mass, so I can fairly ignore the mass. So simply by comparing the angular momentum at the 2 points, I can quickly write it down as r1 v1 equals r2 v2. Since the sine of theta is equal to 1, and we are talking about the same mass, so based on the conservation of angular momentum, we can write it down as r1 v1 equals r2 v2, and v is the velocity at point A and point B. All right, and the second step is we can use the conservation of mechanical energy. Since the gravity is the only force existent in this system, so there should be no loss of mechanical energy, and that means the kinetic energy and potential energy should be conserved. Once when your kinetic energy is now decreasing, and that means your potential energy is somehow increasing. So for the mechanical energy at point A and point B, they should be equal to each other like this. And the mechanical energy is kinetic energy and plus potential energy. So let's keep going. That is the 1/2 mv1 square and plus minus the g times mass divided by the r1 is equal to 1/2 mv2 square minus g times mass and divided by r2. All right, so this is the conservation of of mechanical energy. All right, so I want to write our final mechanical energy in the form of mass and the distance between the planet and sun, or between the satellite and the Earth. So I don't want to see the velocity. Our job is trying to cancel the term of velocity, cancel the v term. So I can use equation 1. If I can express my kinetic energy as something related to the distance, then the job is done. So my way is you can exchange the two terms and combine the kinetic energy term, like the 1/2 m. I move this 1/2 mv2 square to the left hand side. And as you know, the equation 1 tells you that the v2 is equal to r1 divided by r2 m times v1. So plug that in to the v2 square, and I can quickly write it down as v1 square and 1 minus r1 square divided by r2 square is equal to, let's move this g times mass divided by r1, this term to the left hand side, and that will be g times mass and r1 1 over r1 minus 1 over r2. All right, for this term, 1 minus the r1 squared divided by r2 squared, it could be even further expressed as r2 square minus r1 square, and that is r2 plus r1 and r2 minus r1. All right, which is now equal to G times mass, and R1, R2 minus R1. All right. Simply by observing this equation, I can cancel the R2 minus R1 term, and I can further, this is R2 squared, further cancel one of the R2. All right. So, there's a V1 squared. So I can get that the 1/2 mv1 squared, which is the kinetic energy at point A, is equal to R2 plus R1 m times R1 G times mass m times R2. So this is the kinetic energy at point A. So the total mechanical energy at point A could be write down as the mechanical energy at point A is equal to the kinetic energy plus the potential energy at point A. And kinetic energy at point A is 1/2 mv1 squared, which now can be written as something related to the distance and the mass. So let's just combine all of this. The kinetic energy term is G times mass, and for all this, all right, I'll take the same term in front of this. So inside it should be R2 divided by R1 plus R2 times R1, and minus, since the potential energy is minus G times mass and divided by R1, right? So I need to cancel the 1 over R1. I can just take the same term in front of it, like the 1 minus R1, which is now equal to R1 over R1 and times G times mass, and inside it should be R2 divided by R1 plus R2 and minus 1. Let's simply, by observing this term, it should be R1 plus R2 and R2 minus R1 and minus R2. Then just cancel the R2 term and cancel the R1 term, and there's a minus. So the final result is the minus R1 and plus R2 and G times mass. All right, so this is the mechanical energy of the system. Since the mechanical energy is conserved, so it doesn't matter where you are now located. You are now located at point A or point B. That doesn't matter because the total mechanical energy is now conserved, and we have derived the total mechanical energy can be expressed as the mass and the distance. So usually we will call the R1 plus R2 as the average diameter, the R1 plus R2 and divided by 2, and this will be called the average diameter. So I can rewrite this as minus G times mass and divided by 2, or this is so much like a satellite which is now moving around the Earth, and he's circling around the Earth. It doesn't have to be elliptical motion. For circular motion, this is the form that we are familiar with. But now, even you change the circular motion to elliptical motion, the form of mechanical energy is so much like each other. So, thanks for watching, and this is Nash.